Hey, pre-calc students, this is going to be the first lesson of our new unit. Now, it's really just an extension of our last unit 4A, of course, where we were talking about properties of polynomials. And in the last unit, we were looking at polynomials of degree 2, which would be quadratics. So now we're moving on to what I call HOP, higher order polynomials, or HOPs, as I'll call them in this unit. So for higher order polynomials, we're going to be looking at probably degree 3 and higher for the most part. And to get started, we're going to start talking about how do we solve equations and inequalities associated with these functions. So you can see that if I look at this in a factored form, we already have more factors than we're used to for a quadratic. When you have 3 factors, we're going to wind up having 3 roots in most cases, like we would in this case. If I set this equal to 0 and solve, since it's already factored for me, we can easily tell that one root would be at x equals 1. Another root would be at x equals 2 is what would make this equal to 0. And then finally, we would have negative 3. There's not necessarily anything saying you have to write them in order, but I will in a solution set for the first part, just so that we know that when I go to do the next 2 parts, where is this greater than 0 and then less than or equal to 0? We want to make sure that we have the correct roots and in order, because I'm going to have to put those on a number line. So it won't be any surprise to us that to do the inequalities, we have to test where is it positive, meaning greater than 0, and where is this going to be negative, less than or equal to 0, so that we can figure that out from partitioning. So the partitioning process gets extended a little bit further when you have 3 factors. So we've got negative 3, we've got 1, and we've got 2. I'm still going to play the positive negative game, but we have 3 quantities to consider to determine if the overall region is positive or if it's negative. So let's take a look at something like negative 4 to the left of negative 3. Negative 4 minus 1 is negative. 2 minus negative 4, be careful with that, but 2 minus negative 4 is a positive. And then negative 4 plus 3 is negative. So when I multiply these 3 things together, what type of number am I going to get? Well, negative times negative, if I do those 2, that's positive. And a positive times a positive all together is positive. Let's move on to the next section. Zero's in here, so I'll choose 0. 0 minus 1 is negative. 2 minus 0 is positive. And 0 plus 3 is positive. So in this section, we get negative, positive, which altogether is negative, right? Positive times positive is positive, but then if I multiply by a negative, I get negative altogether. Remember, the order for multiplication doesn't really matter. Multiplication is commutative. You can choose whatever pair you want with to start. And if you want to even draw in these partitions, I mean, that's what a partition is, right? It's a separation. That might be nice just so we don't kind of get confused here. Be careful between 1 and 2. We probably should pick 1.5. 1.5 minus 1 is positive. 2 minus 1.5 is positive. And 1.5 plus 3 is positive. So then altogether, this region is positive if I multiply 3 positives together. And then finally, if I choose, let's say, x equals 3, 3 minus 1 is positive, 2 minus 3 is, careful there, negative, right? If I choose x equals 3, but then 3 plus 3 is positive. So with the 1 negative in this region, this altogether will become negative. So I did the partitioning kind of quickly, but it's the same idea as what we had for quadratics. Just 1 extra factor to test in, and maybe just a little bit more to think about as far as, is the overall region positive or is it negative? So where is this greater than 0? Greater than 0, we know we're looking for positive, so that's to the left of negative 3. And it's also in between 1 and 2. So the way I'm going to write the solution to greater than 0 is negative infinity to negative 3. I'm going to use parentheses there because it's just greater than 0, not also equal. And then union 1 to 2. So that would be the solution to when this is greater than 0. Less than or equal to 0, it's the same number line, just looking at the negatives now. And since it can be equal to 0, now you can include those zeros at negative 3 and 1. So it's negative bracket negative 3 to 1. Union, well, it's also negative out here from bracket 2 to infinity. Okay. So hopefully that makes sense, extending the process out just a little bit further. Okay, let's try another one just like it. So for number 2, we're going to do x minus 1 squared times x minus 3 times x plus 2. And I'm going to do two things here. I'm going to do where is this greater than 0 and where is it greater than or equal to 0. Seems like wait, isn't that the same inequality? Well, you'll find in this one that you're going to get actually different answers. Other than brackets, there's something that's kind of weird that happens for this one that we'll see in 1 second. Okay. Now, I didn't ask you where it was equal to 0 to start, to just list off the roots initially, but we can do that anyway because we need them for our partition points. So the partition points occur at positive 1, right? That would make this thing 0. Even though it's squared, 1 minus 1 is still 0. And then that's 3, and then over here, negative 2. So in order on the number line, we're going to put negative 2, and then positive 1, and then positive 3. Okay, so when I go to start doing my testing, both of these I'm looking for positives because we're looking for greater than 0. But in one case, I can include the actual roots, and then in the other case, I can't. So let's go ahead and start testing. Negative 3. Negative 3 minus 1 is negative. However, then I'm squaring that number. So even though negative 3 minus 1 is a negative number, squaring it turns it to a positive. In fact, no matter what I plug in for x here, it doesn't matter what region I'm in, when I square that number, doesn't it always make it a positive? So even though this looks a little scarier to start potentially, it actually makes my job pretty easy when you have that quantity squared. No matter what I plug in, whether it's a negative on the inside or a positive on the inside, squaring it makes it a positive number. So you can carry that across. All right, so then I just have to really test in the other two factors. If I test negative 3 minus 3 is negative. Negative 3 plus 2 is negative. Two negatives multiplied give you a positive, and positive times positive is positive. Okay, in the next section, if I test zeros over here, 0 minus 3 is negative, and 0 plus 2 is positive. So with that one negative, this whole region is negative. If I test 2, 2 minus 3 is negative. 2 plus 2 is positive. So again, we have that one negative, two positives. Don't be fooled by this. You can have negative, negative in a row. Because maybe you're almost thinking in this one, like, oh, is it just going to alternate signs? Positive, negative, down the line? We've already broke the rules here. Positive, negative, negative. What happens out here if I test 4? 4 minus 3 is positive. 4 plus 2 is positive. So actually, this last region does turn positive. Okay, let's talk about where this is greater than 0. It is greater than 0. We're looking at just the positives, so I don't really care about too much about what's going on in the middle here. But it's greater than 0 from negative infinity to negative 2. And then also from 3 to infinity. So kind of on those outside parts. When I do the greater than or equal to 0 step, you probably don't think it's that much different, right? I mean, isn't it the same thing? But now I can just include those endpoints, right? So just put brackets on those and call it a day. Well, the answer to that is not quite. Because wait, isn't it also equal to 0 at 1? So when I'm looking at greater than or equal to 0, I'm still shading here and I'm still shading there. So I can put brackets on these, but I have to also include that x equals 1 makes this a true statement. X equals 1 makes this equal to 0. So it's going to be negative infinity to negative 2 with a bracket, union. The next thing I should include is 1. And usually you see that since it's a singular, it's not an interval, right? It's just that singular value with curly brackets, okay? Union, and then the last part would be 3 to infinity with a bracket. So that's a trickier step, right? I mean, I hope it makes sense logically looking at our number line here. But that's really tough to remember to include that x equals 1 value, okay? So we don't see that come up a ton, but now that we've seen it here, hopefully we'll be able to catch it in the future. If we take a look at maybe just one more example like this, if I gave you x squared plus 1 times x minus 2 times x plus 3, and I want to figure out where is this less than or equal to 0. So we're doing an inequality, which means we need our partition points, okay? It's a little different when the squares on the inside of the parentheses versus the outside like it was in this one. Here, 1 definitely made this equal to 0. Well, what makes this thing equal to 0 here? So if I were to kind of do that off to the side, when is x squared plus 1 equal to 0? Because I know this is x equals 2 and this is x equals -3. But if I solve this, I would subtract 1 to the other side, square root to get x equals plus or minus I. Okay. Since this doesn't have any real solutions that are real numbers, we're not going to put anything on the number line to partition around as it relates to this expression, which actually makes this example pretty nice. There's only -3 and 2 to partition around. So if you have a quadratic that gives you imaginary solutions like this one, then there's nothing on the number line you have to include for that factor. Now, by the way, when you do the partitioning, I guess we should still test in there technically, right? It's still a part of the whole thing. But if I test something in there, what's always going to happen no matter what? I'm going to take something like -4. I'm going to square it and then add 1. Doesn't squaring a number and then adding 1 to it always make it positive? So similar to what we had here, although for different reasons, right? Here we actually had a root to put on the number line. Here we get these imaginary roots. And no matter what I test in this factor, it's always positive. Squaring a number and adding 1, definitely positive. So let's just test in the other two again. So if we test -4, -4 minus 2 is negative, -4 plus 3 is negative. These two would multiply to positive, and positive times positive is positive. Come over to the middle. If I test 0, 0 minus 2 is negative, and 0 plus 3 is positive. With the 1 negative there, we get a negative region altogether. And then finally, to the right of 2, if I test 3, 3 minus 2, positive, 3 plus 3, positive. So altogether, this is positive. What was I looking for? I'm looking for where it's less than or equal to 0. So less than would mean we're looking for the negatives. And you can include these endpoints here. So the solution set is everything from -3 to +2. Now, just through those 3 examples, this will really help you to get through the first homework, but I know that there's some weird things going on here. So of course, if you have any questions about this, you can ask me during the recap, and maybe we'll even do 1 or 2 more for practice. Since you've done the graphing calculator hop lab at this point, what I want to do is maybe just quickly think about some quick sketches here to finish up today's lesson. So when I ask you to sketch, I'm going to give you the roots of a higher order polynomial, and you're going to sketch what the graph looks like. So if I gave you roots of -1, I, and -I, what might the graph look like? Well, it actually could have 2 different appearances. It depends on if the value of a is positive or if the value of a is negative. What do I mean by a? A is the coefficient of the highest powered term. And if there are 3 roots, I know that this example is something with x cubed in it. So if the number out front for a winds up being a positive number, what do I know about the way this graph looks? Well, what I know is that we definitely have a root at -1. But with imaginary roots, we don't quite know what the rest of the graph would look like. I only have enough info to know that we cross the x-axis at -1. So the graph might look something like this. We know that when a is positive, that the tail on the right goes up and the tail on the left goes down. Meanwhile, with a is negative, we're still going to cross at -1, but notice how the tails go in kind of opposite directions now. Right? The tail on the left goes up, the tail on the right goes down. So just make sure you're kind of keeping track of those rules. And as far as what else is happening in the graph, we don't know. All I want to see is that it crosses only at -1 and that the tails are going in the right directions. So if I gave you that the roots of a polynomial are at -3, 0, 4, and 4 again. Okay. So this is a double root. What we know is that if you have 4 roots, this is an equation that has x to the 4th in it. And x to the 4th, we know something about the tails or the ends of the polynomial here. And that's going to look different if a is greater than 0 or if a is less than 0. Let's talk about if a is positive first. If a is positive, for x to the 4th, both tails go up. If a is negative, both tails go down. So let's go ahead and see if we can account for all this here. So we've got -3, +4, and then 0 as the root locations. -3, 0, and 4. But what does the graph have to do at 4 if there's a double root there? What you should have learned from the lab is that it bounces off of x equals 4. So we're going to cross at -3. We're going to cross at 0. But when I come over to x equals 4, we're going to bounce off of 4 and head right back on up. That's how I can look at a graph and know that there's a double root at 4. If it bounces off of 4 rather than crossing through the x-axis. Single root, double root. And again, if a is greater than 0, we got to have both tails going up. But meanwhile, if we had the same situation, but a was negative, -3, 0, 4, same root locations. Just make sure the tail on the left now starts down, cross the x-axis, but when I get to 4, bounce and head right back on down. Okay, so we're bouncing off the axis and going right back down there. Okay. Let's just do maybe one more. We'll do another one with 4 roots. So if I gave you that the roots are at -2, 3, 2 plus or minus I, and I tell you that a is less than 0. So I won't do both cases this time. We'll specifically look at a being negative. Okay. Altogether, how many roots have I given you? I've given you 4 roots. 2 that are real roots, 2 that are complex or imaginary roots, right? You could separate those into 2 different distinct roots. So if a is negative, we actually just did that over here, right? For a 4th degree polynomial, we know that both tails should point down. And we know we're going to cross the x-axis at -2 and 3 only. So -2 and 3 are the roots. As far as what else is happening in the graph, I mean, when you have imaginary roots, there does tend to be some other curvature to the graph. So I know both tails are going to point down. You know, if you don't have anything that has kind of, it usually looks like this M-type shape, but make sure your M doesn't come down and hit the x-axis again. These are the only 2 real locations that we can have. So if your graph looked like this, is that okay too at -2 and 3? Sure, it doesn't look identical to mine, but it has the roots in the correct locations and both tails are going down. So if you in the end have something that looks slightly different than me, that actually can be okay. All right, so we'll do a little bit more practice with this next time I see you, but 2 main ideas from today. We've got to make sure that we understand how to solve inequalities by doing more partitioning. And then just what the sketches of higher order polynomials look like when we have 3 roots versus when we have 4 roots, okay? Hope you have a great rest of your day. Let me know if you have any questions.